Hello, everyone. Good afternoon. And hopefully everyone had a great lunch and now is ready for this talk. I'm Yonshan from Pinterest, where I'm leading a team focusing on caching, persistent storage, and serving systems, and pretty much all online stateful services at Pinterest. I'm very honored to be here today, and there's many really great talks earlier in the morning. I hope you enjoy this talk as much as those talks. So before we get started, I want to just say a couple things very quickly about Pinterest. How many people here actually know what Pinterest is for? Okay, it's a pretty good crowd knows what Pinterest is for. So basically, our mission is really to help people discover and do what they love by building world's catalog of ideas. And our primary sort of real estate items on our platform is a pin. A pin on the surface looks like an image, but it's really a video bookmark saved by our pinners from internet onto Pinterest. So there's content behind all those images. And at this point, we have 100 billion, more than 100 billion ideas or pins on our platform. And we have more than 175 million people using our service. And most importantly, they help us categorize all those ideas into more than 2 billion boards. So there's crowdsourcing, human curation going on our platform, and which helps us understand the content much better. In today's talk, I'm going to cover 3 topics: our journey in the last 6 years and how we scale storage, caching, and then provide key value store and graph storage services for developer productivity, and also how do we scale machine learning serving at Pinterest. And 6 years ago, we got into a phase of a really, really explosive growth. And according to an article on TechCrunch back in 2012, we're actually the fastest growing standalone service in the United States, ever reached 10 million MAU. And obviously, there's a lot of help from other services to refer all this traffic to us, but we grow really, really rapidly. And with all those traffic coming to us, and initially when we built the site, it's just a Python Django app on a single MySQL. So we really, really need to scale our service fast. And the first thing we look at is we have all this data, how do we accommodate all that growth? And the solution we took there is to shard our MySQL tier. And our sharding scheme is kind of interesting, which is that you look at the first few digits of object ID. They basically are reserved for information about sharding. So to tell us where to look for this particular record. And the second part of that object ID is object type. And basically, with this sharding scheme, really, we can co-locate multiple different kind of object into the same shard. For example, if a user owns a whole bunch of boards, and in those boards there's a whole bunch of pins, and they can all co-locate it on a single shard. And when we query them, it's much more performant. And then on the sharding part, we really reserve enough bits so that we can support a ton of shards. The reason why we did that is because we want to make sure down the line we don't have to deal with shard splitting, which is much more complicated to do. And to horizontally scale out, and what we did is that we first just opened a few of those shards to put the users in. And as we grow, we can choose to open more shards to put new users in, their pin, and their boards in. So this is one way to scale out. But then once we have a few thousand shards and they're scattered around on some MySQL instances, there are maybe hundreds of shards on each MySQL instance, then we have the option to migrate out some of the shards to another instance. So there's a couple ways we can use to scale out MySQL tier. And on the caching side, as we add more and more Python Django servers into our stack, one of the problems we run into is that because Python as a process is very, it can only fully utilize one CPU core. For multiple core kind of machines instances, you have to run multiple processes. So there's a multiplication effect of all those processes need to connect to the caching server. And then very soon we hit, the caching server has way too many connections on them. And the way how we addressed it is we introduced a proxy called Time Proxy or Nutcracker. This is a proxy open sourced by Twitter back in the second half of 2011. And this way, we have all those Python processes connecting to the caching proxy. And the caching proxy basically multiplies all those connections down to one connection to the memcache server. And this way, we gradually reduce the number of connections to memcached. And this sort of, and also Nutcracker handles the sharding of the memcache cluster by a form of consistent hash ring. So then you have the horizontal scalability, and at the same time, you don't have the issue of having way too many connections onto the memcached server. One of the things we learned later on is that the caching, the Nutcracker actually really favors availability. What that means is that it adjusts the consistent hash ring once it detects certain host of memcached is not reachable. But it is great. It's highly available, but it causes a caching consistency issue. I'm just going to very quickly illustrate how that happens. So, for example, if there is a network glitch on production, and which caused the caching proxy to eject one of the hosts from its consistent hash ring, and it basically now it will basically reshuffle the assignment of the keys among the rest of the hosts. So let's say full used to be put onto memcached 1, and now let's say after the reshuffle, it's being assigned to memcached 2. Now if there's a request coming in, and try to change the value of full, and now it's going to be putting into the memcached 2. And basically, if the network glitch now is over, and you go back, when you start to serve, you ask for full, and it'll serve value of 1. So this is causing stale data. So if there's a lot of network glitch going on, basically your application is going to be reading multiple versions of the same value. To address that issue, so we are looking for a proxy that doesn't reshuffle the consistent hash ring that fast. And luckily, Facebook open sourced a MacRouter, and which gives exactly this behavior. But if you don't do this reshuffling, that basically means that there's going to be a lot of cache misses. How do you solve this problem? Basically, MacRouter provide another way, which is allow you to have a multiple cache ring. So basically, solving this availability issue by redundancy. And MacRouter doesn't really support Redis, and we use Nutcracker. Nutcracker support both memcache and Redis. Redis provide rich data structure support like hash map and sorted set, and we needed those things for doing pagination, doing partial retrieval. So our way out of it is later on we sort of change memcached to support those data structures. So then we gradually phase out Redis and then be able to get rid of Nutcracker from our stack. So just to quickly summarize, and we scale the persistency storage layer by sharding MySQL. And also, the current status is also we introduced HBase into our stack to handle the write-intensive use cases, because the LSM tree is really good for write-intensive use cases. And on the caching side, we adopted Nutcracker initially, but then we replaced it with MacRouter for better consistency and fault tolerance through redundancy. And we enhanced memcached to support hash map and sorted set. And if you look at our sharding scheme doesn't really support key value use case very well. Like, because the ID could be arbitrarily anything. And we have a lot of use cases where we need to support a key value use case. And because we have HBase on our stack, and HBase is really just a key value NoSQL cluster distributed database. And we're like, that's a good fit to store all this data. It's all horizontally scalable as well. But then quickly we realized that we can't just hand over HBase to the developers to put that data in, because as good as HBase is, there's still time where it's going to go down. You still need to handle it. And the application developers also need to handle caching themselves. And if they have hotkey in their system, they need to handle it. And if multiple use cases are on the same cluster, and how do we deal with, achieve fair failure and failure isolation, and then we put too much burden onto the application developer. So the solution is that we put a service in place, and which is a Swift service on top of HBase, and provide a key value API. But down the hood, we actually use master-master replicated HBase clusters, and we support failover, so to give application developers fault tolerance. And we support it with built-in caching, and we also monitoring the keys that application access, modify, mostly for writes, and this is where HBase actually suffers. If you have very, very rapid writes on the same key, and it suffers. So in that case, you need the throttle. And we have the support for it, and which allow us to avoid abusive application to take down the entire cluster. On the multi-tenancy side, we monitor every single use case, their space utilization, the read and write QPS, and once they're over their allocated quota, and then we'll start to limit them. It's great that we provide key value storage as a service, but can we do better? What I mean is that if you look at a lot of applications, to model those applications to use the key value is really, really hard. And I can give you an example. So this is one of the features we rolled out on our service, which is a message service. So there you have multiple users participating in the same conversation, and each conversation could have multiple messages. So it looks pretty simple, right? But if you really think about it, if you wanted to support it with a key value, and now you need to very carefully design your key to be able to actually support this. Now there's also paging it through all the messages in the conversation. There's also maybe index support you need. For example, if I want to look up a conversation associated with a particular pin or a particular board, and then I need some sort of a global index to support lookup. And okay, it's hard with key value, but how about put this into Sharding MySQL, right? It should be okay. But if you think about it, even there you need to go through a lot to put all this stuff onto production. It's very easy for this type of application developer to spend days to actually just get the data model and all the coding, doing the CRUD in place on production. And one of the realization we had when look at all this data modeling issues is that you can view all the try to model this with a graph, and objects are basically nodes in the graph, and the relationship among the objects are really just the edge connecting them. And once we realized this, and we're like, maybe we can support all those use cases with a graph store. And that's our graph store is named Zen. It's actually inspired by Tau. Tau is kind of a similar kind of system at Facebook. And what Zen does is that it opens up the API to the application developer. You can go create node type, edge type. You can go create indexes. It's just kind of like as a database where you go create a table, create indexes on the attributes of the table. So when the application developer need to put in the data model in place, they just call these APIs instead of having to talk to the DBAs. And there's quite a few other things that's being supported there, which make it much easier to write application. And we also support MySQL and HBase backend to handle various different kind of load pattern. So now, quickly on the graph sort of model to model the message application I mentioned before. Here, basically, you have user as a node type. You have conversation as a node type. You have message as a node type. And the participation relationship basically is just an edge between user and conversation. And the contains a relationship between conversation and messages are really just also a new edge type. So if you need to look up the user based on their name or their email, that's just a global unique index. And if you want to, there could be many conversations associated with a particular pin because I can send it, user A can send a pin to another person. User B can also send the same pin to another person. So, and if you want to see who are the person ever send this pin to another user on our platform, you can basically use this global non-unique index to look it up. So now application developers only need to do is just call a whole bunch of APIs to create a data model, and then they can start just pretty much focus on their application logic. Some of the numbers, basically both graph store as a service and the key value as a service are very successful at Pinterest. On the key value store side, we have more than 100 use cases. We're serving close to 1 million QPS. On the graph store side, we have more than 10 clusters. Some of the clusters are multi-tenancy. Some of the clusters are for really big use cases that are dedicated. We store collectively, we store about petabytes of data on it. We're serving close to 10 million QPS. And so this really saves a lot of time of our engineers and allow them to focus on product innovation instead of just a basic wiring. And so what we kind of realize is that as the infrastructure team, what we do is that we need to embrace the challenges on scalability, availability, reliability, performance, efficiency. And as a persistent storage tier, you also need to worry about durability and consistency, right? So once we embrace those challenges, and then we basically free up our developers to focus on product innovation, focus on feature, and instead of all the basic wiring. So this is a great boost to the productivity. This is basically instead of scale your architecture, this is the key to scale your organization. And now I'm going to be switching gears and start to talk about machine learning serving. Where is machine learning serving used on Pinterest? Because Pinterest, our mission is to help people discover and do what they love. And part of that is to recommend relevant content to people. And how do we know a particular piece of content is relevant to a particular user? And machine learning is what's helping us achieve that. And another, so we first introduced machine learning for ranking back in 2014, and we see the largest metrics gain ever. And nowadays, we really have a lot of machine learning and serving going on our platform. We serve hundreds of models, and they score tens of millions of candidates every second. And one of the primary real estate of Pinterest is the home feed. Home feed is you have a whole bunch of pins. Some of the pins are what we recommended to you. Some of them are based on the users and boards you follow. It's kind of like a Twitter. You follow people, and as they produce content, you see them. So initially, when we generate our home feed, we generated it in a sort of offline manner. What I mean is that the home feed is not being assembled together at the time when the user come to the home feed page and say, give me my home feed. It's actually happened when the content gets created. It's more like a push model. And when new content gets created, based on whether it's coming from the following or because we think it could be relevant to you, and they're then being scored by different ranking models. And then they're being put into a pool where they are being ordered by the score produced by a ranking model. So this is not online. There's no user waiting. So this is what I mean by offline generation. And then on the runtime, when people actually come for our home feed, and then there's a blender which pick the content we put into the pools and then assemble them together and put it into home feed. So now, if there is a slowness in this blender part of the stack, and somehow we couldn't produce the recommended content, we still have home feed materialized. We still, people wouldn't see a blank screen. So this is when you think about it, is a reasonable architecture for achieve really high availability to serve home feed. But and the model scoring part at this stage of our application is rather naive. Because this is really an offline use case. You don't need like super good latency, and you don't need like high availability, because if it goes down, the worst can happen is that for a few minutes there's no recommendation to people. But then but they can still see what they used to have in their home feed. So high latency offline use case, and then here we just do it very, very naively, and we just say, go fetch all the data remotely, and if you ask me to score in 1000p in the request, I'll just score them sequentially. And at this point, also the model are handcrafted Java code. When we fetch the data and we need to do feature extraction and fit that into the model, all the stuff is done manually. And the next part is that we introduce a DSL into the stack. The code name is linchpin. So the DSL is basically a domain-specific language. So why do we do this to replace the handcrafted code? Is because if you think about it, if you write the code, the code has to be compiled and running for a particular language platform. And if you, over time, evolve your infrastructure, let's say in our case, later on I'm going to show you, is that we are nowadays all our scoring services in C++. So going from Java to C++, if you use handcrafted code, then you need to rewrite all that code, right? But if you use the DSL, as long as the interpreter can interpret, and then you don't need to change anything, it's still going to work. The other part is like, you have this tangible model as a text file. You can still ask the people to review it. You can check it in. You can version it. Another advantage is that you can deploy it as a configuration, and you don't need to deploy it as a binary. And so there's no service restart is needed. And for example, you can give a model ID to a particular model, and then as it's being loaded as a configuration, the request come in and say, score it to use that model, and it just works. So I'm going to go back to the offline generated home feed. Although it's good, it has a lot of problems, because the main thing is that there's a gap between the time when the content is being scored and when the content is being consumed. And let's say if a user is infrequent, is weekly active, he comes in every week, and there could be content which is being scored on Monday. By the time he comes in on Sunday, maybe his interest changed. Maybe the model itself changed, right? So let's say we deploy model on Wednesday. If somehow the scoring of that model is not exactly the same as how the model we used to score some piece of content before. Like how do you reconcile all that stuff, right? So ultimately, what we want to achieve is that we want to give people the most relevant content at real time. And also, there's no normal. So I show you a couple pools, right? So there's no. Each of them has its own model. So this there's no normalization, and there's a lot of art goes into how Blender works. And also at the same, because it's a push-based model, all those pools are being constantly maintained for our users. Even if they don't come visit, we still push all that stuff into that pool. So there's a lot of computation resources being invested for inactive users or people who are not visiting our services all the time. So how do we address this problem is that we wanted to evolve our home feed from sort of a more like an offline generated way, push-based way, to a pull-based, fully online way. So we only generate your recommendation when you come actually ask for a recommendation. But now you think about it, it's no longer offline use case, it's online use case. So our original service is very slow, it's not capable of doing this. And also it fetches everything from remote is very, very network intensive. Network has basically become the bottleneck. So what we replaced it with is real pinnability. What it does is that first of all, it has the root and the leaf nodes. On the leaf node, where we store all the data there. So basically, it's also kind of distributed system. It's many, many shards, and it's being distributed on it. The primary sort of feature needed for scoring are the pin metadata. So when the root node making the routing requests, routing decisions is based on that. So let's say we need to score 4 pins, and pin 2 and pin 3 is on machine 2, and pin 1 and pin 4 on machine 1. Then we make the routing decision that way, and then those machines are going to retrieve other data needed, necessary among its peers. So all the data is all contained in that cluster. And all this data is being stored in RocksDB. So it's an embedded database, and this allows us to co-locate the compute, the ranking, with the data. So, and also, as you can see, there's now scoring being done in parallel. So basically, as many sub-requests is sent from the root is how much the parallelism is there. So now this service is also being written in C++ to give us better efficiency because it's very, very compute hungry. It actually saves a lot of cost, and also it's better in terms of long-tail latency. But now with this, a lot of the application developers actually complaining about, although this is very, very efficient, very, very good, but because we co-locate the data with the compute, we need to upload all the data up front onto this cluster. So if they wanted to have the model use new features, then we now need to load more data onto it. And another thing is that in terms of the efficiency, we couldn't scale the compute and data independently. So there's efficiency cost there. To address those concerns, we replaced with the Scorpion. Basically, the main differences there is that we no longer strongly co-locate the data into the serving tier. Instead, we cache the data there, so that we still, if the cache hit rate is reasonably high, we still co-locate the compute with the data. But there's no such a strong correlation of the data and the compute, so it makes it much easier for us to scale that tier. Scorpion is actually that serving is actually one part of a unified serving and training system we're building across the company. And so through that system, what we want to do is I want to tie the serving and the training and the logging and the labeling and all that all together, and then provide it as a unified platform to serve all different kind of use cases. There again is what we want to do is that we embrace the complexity, but we give our engineers the time to focus on innovation. So just very quickly recap. Initially, when we get started, we have pinability, which is offline, which is network intensive. And then we move from offline to online, where we need something that's really, really fast and co-locate the compute. And we did that by co-locate the compute with the data. And then next up is we need to bring back that flexibility back into our system. That's where we choose to co-locate the compute with data through caching. So fundamentally, it's re-embracing the data fetching from remotely again. Okay, just to recap of those 3 topics I talked about today, and we scaled the persistent storage tier by shedding MySQL, and we scaled the caching tier by introducing the caching proxy. We provide this key value and graph store as services to boost developer productivity, which allow us to scale with our org growth. And I also talk about our journey from sort of the initial very naive implementation of machine learning serving to a unified machine learning serving and training platform. That's all I have for today. Thanks a lot for coming to the talk, and I'd like to open up for questions if people have any.
Hi, so I have a quick question. Do you apply deep neural networks in your machine learning stack?
Yes, we do, because a lot of so recently we have a release of something we call pin lens. Basically allow you to take a photo and then we recognize what's in there, and then we perform a search and bring sort of the recipe and a lot of interesting stuff to you. Image is a core part of our service, and we invest a lot to try to understand what's in it.
Is that handled by this same stack? Or
yes, because you have the model, and then you just need to load that model into the serving platform, and then you fit the features in, and it tells you what it is.
Hi, question about your recommendation system. Are you generating recommendations specifically for each user, or do you generate recommendations based on some intermediary representation, such as a category or something along these lines?
So I think we do both. So one thing I didn't go to much detail about is the candidate generation part. So for example, on Pinterest, we also offer topic. So you follow the topic. And what's in the topic is actually, I would just say, generic to everybody. But at the time when the content is being retrieved, the ranking is personal, is personalized. So although the candidate pool is the same, but what is actually being serviced to you is very much based on your interests. And then there's certain things that is highly, highly personalized. That's just one example.
Thank you.
No more questions? All right. Thank you.